The Arabian Sea at 4:06 a.m. holds no particular menace in its appearance. The water is dark, the sky is clear, the stars are the specific stars of the northern Indian Ocean at this time of year. Scorpius low on the southern horizon, Orion setting in the west, the Milky Way overhead in the particular density that only exists when you are far enough from shore that the land's light cannot compete with it. A sailor on the bridge wing would find it, under other circumstances, beautiful. The crew of USS Philippine Sea were not attending to the aesthetics of the night. They had been at a modified general quarters posture for 4 hours, since the intelligence update that had come in at midnight and that the watch team had been living with since. Not ignoring, not dismissing, but managing in the particular way that sustained threat awareness requires, staying sharp without burning out. Maintaining the precision of attention that the next 4 hours would need. The intelligence update had described a weapon, not a specific inbound threat, not a report of imminent launch, not a warning that the Philippine Sea specifically had been targeted. It was a capability assessment, the first confirmed operational employment in a theater context of the Iranian Shahed 238. The Shahed 238 is not the loitering munition drone that the world had become familiar with from the campaign in Yemen and the land war in other theaters. It is not the slow, propeller-driven subsonic platform that a sailor watching the radar scope learns to recognize by the distinctive way it moves. The unhurried, wave-skimming persistence of a weapon that trades speed for endurance and is willing to take its time. The Shahed 238 is what the Iranian defense industry produced when it took the Shahed 136's concept and replaced the piston engine with a small jet turbine. A development that increased the airframe speed from under 200 kilometers per hour to well above 900, and that the intelligence community had been tracking through a combination of imagery of the test facilities at Kashan, signals intercepts of the development communications, and the particular kind of backward inference that comes from watching a state invest in a capability and reasoning about why. The confirmed operational employment the midnight update described had occurred in a different theater, against a different target. The weapon had been used once, in a context that the intelligence community assessed as a proof-of-concept operational test rather than a full-scale deployment. The assessed performance had been consistent with the technical characterization that the development tracking had produced. A jet-powered airframe with a cruise speed above Mach 0.8 and a terminal speed in a shallow dive terminal approach that the analysis estimated at Mach 2 or above. A weapon that moved at Mach 2 in its terminal phase was not the same category of problem as a weapon that moved at 200 kilometers per hour. It was a different category entirely, one that required a different defensive architecture, different engagement timelines, and a different set of calculations about what was possible and what was not. The Philippine Sea's watch team had been told in the intelligence update that the Shahed 238 had been assessed as exceeding the SM-2's reliable terminal engagement envelope at the speeds and approach angles the weapon was capable of. Not impossible for the SM-2 to engage. The standard missile family had been used against supersonic targets before, and the Block 3B variant carried by the Philippine Sea had been specifically upgraded for higher speed engagements. But the engagement probability against a Mach 2 terminal approach at low altitude on the timeline that a close-range detection would provide was not the comfortable number that the watch team had been working with against the subsonic drone threat. It was a number that placed more weight on the Phalanx than any previous threat assessment in this deployment had required. The watch team knew this. The TAO had briefed it at watch change. The Phalanx operators had run their system checks twice in the preceding 4 hours. The defensive posture was correct for the assessed threat. The assessed threat had not yet arrived. At 4:06:11 a.m., the SPY-1B detected the launch, not from the Iranian coastline, from an azimuth that placed the launch origin at the coordinates of a semi-submersible launch platform. The intelligence community's assessed deployment method for the Shahed 238 in maritime strike roles, a platform that could be towed to a forward position and operated remotely, presenting a minimal radar cross-section at rest and no thermal signature until the moment the drone's jet engine ignited. The semi-submersible platform had been in the water for an unknown period before the launch. It had not been detected. It had not emitted. It had been waiting at the position it had been towed to, and it had waited until the Philippine Sea's track placed it at the optimal range for the Shahed 238's terminal energy to be maximum at the point of hull impact. The launch generated a thermal signature on the infrared sensor array that the fire control system resolved in 0.4 seconds as a jet-powered airborne contact. The velocity profile from the first 3 radar returns, taken at the system's maximum scan rate, separated by fractions of a second, established the contact's acceleration profile as consistent with a turbojet-powered airframe. The fire control system's threat classification algorithm assigned the contact a threat category that the TAO had not seen assigned to an actual real-world inbound contact in this theater before. Category Alpha, high-speed airborne inbound, Phalanx primary defense. The classification was correct. The system had assessed the contact's speed and trajectory and had determined in its processing logic that the SM-2 intercept probability against this specific contact at this specific geometry was below the threshold for primary commitment. The standard missile would be fired, the auto special mode would commit it automatically. But the fire control system's own assessment was that the engagement's primary burden lay with the terminal defense system. The SM-2 fired at 4:06:13 a.m., 2 seconds after detection. The Shahed 238 was at 22 kilometers range. At its current speed, the time to impact was 31 seconds. The SM-2's intercept point would be at approximately 14 kilometers, the midpoint of the closing geometry. In approximately 16 seconds, the SM-2 missed, not by a wide margin. The intercept occurred within 200 meters of the contact. But the Shahed 238's terminal approach profile combined a shallow dive with a lateral jinking maneuver that the fire control solution had not been provided enough track history to fully characterize. 16 seconds of track data on a Mach 2 airframe is not the same as 16 seconds of track data on a subsonic contact. The geometric information accumulated in those 16 seconds was the same in absolute terms. The same number of radar returns, the same quality of position data. But the extrapolation forward from those returns to the intercept point required predicting the position of a contact that was moving fast enough that small errors in velocity estimation translated into large errors in predicted position. The intercept missed the contact's predicted position because the contact's actual position was 200 meters from its predicted position at the moment of intercept, and 200 meters at Mach 2 is a very short time. The Shahed 238 was at 8 kilometers in closing. At Mach 2, 8 kilometers is 12 seconds. The Phalanx acquired the contact at 4:06:26 a.m., 13 seconds after detection, with the contact at 7 kilometers and the remaining time to impact at approximately 11 seconds. The CIWS track was solid. The contact was large enough on radar at this range to produce a clean, stable return that the tracking algorithm processed without ambiguity. The system computed its engagement solution and began firing at the optimal range for the 20mm round's effective velocity against a Mach 2 contact. The physics of a Phalanx engagement against a Mach 2 target are specific and demanding. The 20mm tungsten penetrator rounds leave the barrel at approximately 1 kilometer per second. The target is approaching at approximately 680 meters per second. The closing velocity between the round and the target is therefore approximately 1 kilometer 680 meters per second. Faster than either the round alone or the target alone, which is the aspect of the engagement that works in the CIWS's favor. The aspect that does not work in its favor is the prediction problem. At Mach 2, the target travels the distance between successive firing bursts faster than the system's round-to-round tracking correction can be applied, which means the CIWS is always firing at a point that the target is about to pass through rather than a point the target is currently at. This is true of all gun-based terminal defense systems against fast-moving targets. It is managed through the system's lead angle computation and the density of the round stream. Enough rounds in the air on the predicted track that the probability of at least one impacting the target before it reaches the hull is acceptably high. Acceptably high is not certain. Against a Mach 2 contact at the ranges available in this engagement, the CIWS operators understood the arithmetic as well as the system did. The first burst impacted the shahed 238's airframe at 4:06:28 a.m. 2 seconds into the engagement with the contact at 4 kilometers. The impact disrupted the drone's jet intake, partially collapsing the intake geometry and causing a reduction in the engine's thrust output. The airframe yawed left by 11 degrees, not a course change induced by guidance, but the aerodynamic response of a damaged airframe to a changed thrust vector. The yaw moved the impact point off the center line of the approach vector. The Phalanx tracking algorithm updated the fire control solution for the new bearing in 0.3 seconds and the mount trained to compensate. The second burst impacted the airframe at 4:06:29 a.m. 1 second later with the contact at 2.4 kilometers. This burst reached the fuel system. The shahed 238 was not carrying a large fuel load at this point in its flight. It had expended most of its fuel on the approach, but what remained was sufficient to ignite when the 20mm rounds breached the fuel lines. The ignition produced a secondary fire in the airframe that the drone's remaining aerodynamic structure could not accommodate at its current speed and altitude. The airframe began to break up at 4:06:29 a.m. while it was still 2 kilometers from the hull. The breakup did not produce an inert debris field. A drone airframe breaking up at Mach 2 kilometers from a ship produces a debris field that is not moving at walking pace. The fragments, some large, some small, some carrying the residual kinetic energy of the jet-propelled approach, continued forward along the general axis of the original approach vector. The fragmentation pattern dispersed laterally and vertically as the airframe lost structural coherence, with the largest fragments retaining the most kinetic energy and the smallest fragments decelerating most rapidly in the air. 3 significant fragments reached the Philippine Sea. The first struck the water 120 meters off the starboard bow and detonated. The drone's warhead, triggered by the impact with the water surface, producing a pressure wave that reached the forward hull as a sharp concussive load that was felt from the bow to the CIC and that cracked the forward optical sensor housing without penetrating the hull. No flooding, no fire. A shock that the damage control board logged as a minor hull event and that the watch team in the CIC absorbed through their feet and seats without losing track of their displays. The second fragment struck the port anchor hawse, the opening in the bow through which the port anchor chain passed to its windlass. The fragment was a section of the drone's engine housing, dense, roughly cylindrical, approximately 40 centimeters in length, and still moving at several hundred meters per second when it reached the ship. The hawse opening was not a primary structural member, but it was an opening in the hull, and an opening in the hull struck by a 40-centimeter section of jet engine housing at several hundred meters per second becomes a larger opening. The fragment passed through the hawse, through the chain locker, the below-deck space where the anchor chain was stored in its bitter end configuration, and into the forward void space below the chain locker before its remaining energy was absorbed by the void space's outboard frame. The chain locker was not a manned space. The chain locker was also directly adjacent to the forward fuel tank, the tank that stored the ship's reserve aviation fuel for helicopter operations. The forward void space that the fragment had entered was the structural space between the chain locker and the outer hull, and it was below the waterline. Seawater began entering the forward void space through the enlarged hawse opening at 4:06:32 a.m. 3 seconds after the Shahed 238 breakup. The third fragment struck the bow deck at a shallow angle and skidded forward across the non-skid surface, leaving a 26-meter gouge in the deck coating before going over the bow. No penetration, deck damage only. The flooding in the forward void space was being reported to DC Central by 4:06:41 a.m., 9 seconds after the hull event. The damage control officer had the flooding alarm and the chain locker access report simultaneously. The void space was flooding through the enlarged hawse opening. The chain locker itself was intact and dry, and the forward fuel tank adjacent to the flooding space showed no signs of contamination on the fuel monitoring system sensors. The structural separation between the flooding space and the fuel tank was intact. The flooding rate through the enlarged hawse was dependent on the geometry of the enlargement and on the waterline height of the hawse relative to the sea surface. The hawse opening in the bow was positioned at a height that placed it above the waterline at the ship's current draft. It was a deck-level opening, not a below-waterline opening, and under normal conditions it was well above the sea surface. Under normal conditions, a ship's bow moves through a swell cycle that periodically puts the bow lower in the water than its nominal waterline. And at the sea state currently running in the Arabian Sea, Beaufort 4, manageable but not flat, the hawse opening was intermittently submerged as the bow pitched into successive swells. Each submersion admitted a pulse of water into the void space. The pulses were not continuous. They were episodic, timed to the swell period, but their cumulative effect was a rising water level in the void space that the damage control team needed to address before the water level reached the frame height, where it could migrate into the chain locker and from the chain locker to the spaces above. The forward DC team reached the chain locker access at 4:07:19 a.m., 38 seconds after the hull event. The team leader entered the chain locker and assessed the situation from inside. The fragment had passed through the hawse and into the void space below. The chain locker itself was dry and structurally intact, and the flooding was entering through the hawse enlargement, now approximately 50 centimeters in its widest dimension. On the episodic cycle of the bow's swell motion, the temporary sealing approach for an enlarged hawse was not a standard hull patch problem. The hawse was a purpose-built opening in the bow, lined with a steel sleeve that guided the anchor chain. Sealing it required filling the opening with material that could resist the intermittent hydraulic pressure of the swell pulse, while leaving the chain in place. The chain could not be removed at sea without an anchor handling evolution that would take the bow crane and 30 minutes of work that the current situation did not provide. The chain occupied the center of the hawse sleeve. The enlargement was around it, in the irregular geometry that the fragment's transit had created. The team leader used a combination approach. Hydraulic bladder material cut to size and packed around the chain on the interior of the hawse sleeve, held in place by a fabricated steel backing ring that could be seated against the interior of the sleeve and bolted to the chain locker bulkhead framing. The backing ring required fabrication. It was not a standard kit component because standard kit components were not designed for this specific geometry. The team leader called DC Central with the dimensions at 4:08:02 a.m. The fabrication team in the forward repair locker began cutting and drilling the backing ring at 4:08:14 a.m. The flooding rate during the fabrication period was managed by the portable submersible pump that the secondary flooding team deployed to the void space access at 4:08:30 a.m. The pump could not fully keep pace with the episodic swell pulses. Each pulse delivered more water than the pump could remove between pulses, but it was reducing the net rise rate from the unmanaged rate to a rate that gave the fabrication team the time they needed without allowing the water level to reach the critical height. The fabrication team completed the backing ring at 4:17:49 a.m., 9 minutes and 35 seconds after beginning fabrication. The ring was delivered to the chain locker at 4:18:03 a.m. The team leader seated the hydraulic bladder packing around the chain in the hawse sleeve, positioned the backing ring against the interior of the sleeve and drove the bolts into the pre-drilled holes in the chain locker bulkhead framing at 4:19:11 a.m. The bladder was inflated at 4:19:22 a.m. The flooding pulses from the swell cycle ceased at 4:19:22 a.m. The episodic pulse loading against the sealed hawse produced a residual flex in the bladder material that the inflation pressure was sufficient to resist. The pump in the void space continued operating, removing the water that had accumulated during the 16 minutes of unmanaged and managed flooding, and brought the void space to dry status at 4:31:17 a.m. The flooding was declared fully controlled at 4:31:17 a.m., 24 minutes and 45 seconds after the hull event. The second fragment had also required attention in a different form. The fuel monitoring system's assessment of the forward fuel tank's integrity had been confirmed by a physical inspection that the forward engineering team conducted at 4:09 a.m., entering the tank inspection access and visually confirming that the structural separation between the void space and the tank was intact, that no fragment material had penetrated the tank boundary, and that the fuel inside was uncontaminated. The inspection took 11 minutes. The confirmation went to DC Central at 4:20 a.m. Forward fuel tank intact, no contamination, no structural compromise. At 4:32 a.m., the Philippine Sea's tactical picture was clear. The Shahed 238 had been destroyed. The debris field had produced 3 hull events, one of which had caused flooding that was now controlled. The forward optical sensor housing required replacement from ship spares, a 2-hour task that the electronics team began at 4:35 a.m. The hawse seal required post-event confirmation every 4 hours for the remainder of the deployment. The bow deck damage was cosmetic. The ship was fully operational in all combat systems. The semi-submersible launch platform was located by the P-8 Poseidon on barrier patrol at 4:44 a.m., identified from its thermal signature at the surface after the drone launch had depleted its thermal camouflage. The platform was rendered inoperable at 4:51 a.m. by a surface engagement authorized by the fleet commander. At 5:15 a.m., the Philippine Sea transmitted her post-engagement status report. The fleet commander read the report and forwarded it with a single added notation to the Theater Intelligence Analysis Cell. The Shahed 238 had been employed operationally in the maritime domain. The characterization of its seeker architecture, its terminal maneuver capability, and its debris field behavior at Mach 2 breakup was now empirical rather than assessed. The intelligence community's model would be updated. The defensive architecture for the next engagement would be updated. The gap between the SM-2's assessed performance and the weapon's actual approach profile would be closed in the next software cycle. All of this was correct and would happen. The Philippine Sea's crew had provided the data for it at the cost of 24 minutes of flooding in a forward void space, and a hawse seal fabricated in a forward repair locker by a team that had never fabricated that specific component before and would not need to fabricate it again, because the component they had built would be added to the standard kit carried by every cruiser in the fleet by the time the Philippine Sea returned to Bahrain. Here are the numbers when the post-engagement assessment is filed and the watch continues. 31 seconds from detection to impact. The total engagement timeline, 2 seconds from detection to SM-2 launch, 200 meters. The SM-2 missed distance against a Mach 2 terminal approach, 2 seconds of Phalanx engagement before airframe breakup at 2 kilometers. 3 significant fragments reaching the hull, 50 centimeters. The enlarged hawse dimension after fragment transit, 9 minutes 35 seconds to fabricate a non-standard backing ring from raw stock. 24 minutes 45 seconds from hull event to flooding fully controlled. 0 fatal outcomes among the crew. 1 launch platform located and rendered inoperable at 4:51 a.m. 1 capability gap documented, characterized, and forwarded for fleet-wide defensive update. The Iranian engineers who developed the Shahed 238 had identified the precise gap in the Aegis defensive architecture that their weapon could exploit. The Standard missile family was optimized for the threat envelope that had existed for decades. Subsonic cruise missiles, medium-speed ballistic reentry vehicles, drone airframes flying at speeds where the SM-2's engagement timeline was sufficient for a reliable fire control solution. The Shahed 238 fit into none of those categories. It was designed to arrive at Mach 2 from a detection range that gave the SM-2 a 16-second engagement window against a target moving fast enough to make 16 seconds insufficient. The gap was real. The weapon used it correctly. What the gap did not account for was the Phalanx engagement that broke up the airframe 2 kilometers from the hull, or the debris field assessment that positioned the DC team at the chain locker access within 38 seconds of the hull event, or the 9 minutes and 35 seconds of fabrication in a forward repair locker by sailors who had never made that specific component and who made it correctly the first time because they knew their tools and their materials and what was needed from both. The gap in the defensive architecture will be closed. The sailors who held the line while it was open are already on watch for the next one.